talked about in the last movie, choosing the system is really important, and in particular it's important for solving problems using conservation of energy. Here are some helpful guidelines in helping you decide which parts of the system you should include in order for doing conservation of energy problems. First, you should include all objects that have the speed changing. So the system should include these moving objects because their kinetic energy is changing, and you can include that kinetic energy as part of the energy of the system. You should also include the object if the height of the object is changing. And in this case, the system should also include the Earth or the surface that they're away from, because then you can include the potential energy which is stored in the gravitational potential energy. And you'll see some examples of that later on, probably in the next set of movies. Later on in the semester, we'll be doing springs, and you'll be able to use conservation of energy in order to solve problems about springs, and we'll talk about that more later. And then finally, if there's some sort of friction in the problem, then you should include the object and the surface on which it slides or rolls so that you can include the friction. And as you know, in this case, the energy will be lost due to thermal energy as the object slows down on the friction surface. So usually for most of the problems that we're going to do, you can really pretty much just think about their kinetic energy and some sort of potential energy or stored energy. In this case, we'll call that kinetic energy K, and we'll call that potential energy U. Most of the problems that you'll solve, not all, but many, will have a kinetic energy K, and the potential energy will be due to gravity, so it will be U sub G. When energy is being lost from the system, then we know that the change in kinetic energy plus the change in potential energy is equal to the work. But if the system is isolated, so it's not interacting with its surrounding, it's not losing any energy due to work, then the work is zero, and that means that the change in the kinetic energy plus the change in the potential energy is equal to zero of that system. Many of the problems that you will do will be like this. Typically, if a system is going to be losing energy to work or to thermal, then it will be done by some sort of friction or some sort of external force, such as tension or something like that. We can do some types of problems pretty straightforward without using conservation of energy. We can calculate the work that's done by a constant force F. And as we said earlier, we're going to define the work mathematically. So this is the mathematical definition, which is that the work is equal to the force times the displacement. So in this very simple example, we have a block. It's going to be pushed by a force F, and it will be moving a constant distance. And again, this force will be constant, which means that the block will actually be accelerating. And the work that's done by that force as it accelerates is equal to F times D. Just to be clear, the unit of energy for work is the joule, which is a Newton meter. That makes sense directly from this equation because the units of force are newtons, the units of displacement are meters, and so therefore a Newton meter is the unit of energy, which is joules. If we have another example, let's say we have this guy, he's attached to a glider, and you can see that the kite of the glider is actually moving at an angle, but he is of course moving horizontal. He's not actually being pushed up in any way. Then his displacement is going to be horizontal, but the force that's acting on him is kind of up and horizontal. Only the horizontal part of the force will actually be doing any work. The vertical part of the force will not be doing any work. This makes sense because that vertical part of the force is being balanced by his weight in the opposite direction because he's not accelerating in the vertical direction at all. So again, if we take that force and we think about his displacement D, you can see that there's an angle theta that's between them. And in this case, this angle theta is important because we really only want the component of the force that's parallel to this displacement d. So in this case, only that horizontal component of the force is actually doing any of the work. And so we can figure this out, and because the horizontal part of that force is actually F cosine theta, so that means the work in this case is equal to F times D times cosine theta. And just be a little bit clearer about that, again, you can break down this force component into a vertical and a horizontal. The vertical component, again, is not doing any work, but the component that's parallel to D, or in this case it's the horizontal, is actually doing the work. And so that component is F cosine theta. And so putting this all together, we can see that you get the work is equal to F d cosine theta. Thinking again about the block that we had in the last example, you can think that when the F, the force vector, and the displacement vector point in the same direction, then you know that theta is 0. And you can remember that the cosine of 0 is actually equal to 1. And so this is actually the most general equation for work that you will have in this class. And as long as you keep in mind what that angle is, theta, if it's equal to 0, then you know cosine of 0 is 1, and you recover the equation that we had in the previous slide. We'll talk a little bit about kinetic energy and potential energy. We can define the kinetic energy of an object of mass m that's moving at speed v by this equation. K is equal to 1/2 mv squared. The guy we saw at the very beginning of the first video, Leibniz, almost had the exact definition for kinetic energy. He actually said it was mv squared. He left off the value of 1/2. So this idea of the kinetic energy has been around for hundreds of years, and it's always proportional to v squared. I want to point out that v squared, speed is the v. Remember that velocity has a direction, but when you square a velocity, it actually no longer has the direction because -1 squared is +1. And so that means, in fact, we can just use the speed for the kinetic energy. We don't have to worry about the direction of the velocity. We can also talk about the gravitational potential energy. Again, most of the problems that you'll do in this class, we'll talk about the gravitational potential energy. So if you have an object of mass m and it is at a height y, then its gravitational potential energy is mgy. And so again, if you plug in all of these, you can see that the unit is a Newton meter, which is a joule. And remember, a Newton is a kilogram meter per second squared, so a joule is a kilogram meter squared per second squared. And again, if you plug this into either one of these equations, you get the same units out.